All right, good morning everyone. So let's get started on this chapter again. So where we left off last time was this heat conduction. So I think this is a good place to start again. So just to recap, what we were talking about there was if you have some material, you can work out how much energy is transferred through this material according to this particular formula here. So this is the power, and basically there's more energy that's transferred if the surface area, the cross-sectional area of this material is larger. So the larger this is, the more energy is transferred. The longer this is, the less energy is transferred, so it's inversely proportional to this. So if you've got a long stick here, then the energy that you get through conduction is very low. And finally, also there's a hot end and a cold end, and obviously the bigger the temperature difference, the more energy is going from the hot end to the cold end. And what we did last time was to look at this particular situation, which is a classic case or classic kind of question that you get for this type of, for this particular concept. So you look at a composite slab with different thermal conductivities, and basically the thing that you need to know here is that the power that is going through this, so long that the dimensions are the same, and usually they are, so for example the cross-sectional area here is the same, then the power that goes through them is going to be equal, because obviously you can't just have energy kind of lost to the side. I mean, you could, but I mean, if this is large, then generally we don't think of that situation. And then, so basically the power that's going through material 1 is the same as material 2, so you can basically equate these things. And then usually the question is something like, what is the temperature at the interface of these two materials? So if there's material 1 and 2, then we're trying to find what the temperature here is, right? And again, so the way that you do that is that you say that the power is the same, and then there's some algebra that you need to do to eliminate, you equate these on, and then to find this interface temperature Tx. So that's a little bit of algebra after you equate these ones. And then once you've found that temperature, then, for example, then you can find also the power. So if the question is then, what is the power that's gone through here, then you can substitute that Tx back into here. Then you should have all the variables on the right-hand side that you can figure out the power. So worth doing a few practice questions on this one, but I think maybe we'll move on from here. So just to get some intuition on this. So the figure shows the interface temperature of a composite slab. So there's actually four materials stuck together, consisting of four materials of identical thickness. So this thickness is the same, through which the heat transfer is steady. So these temperatures are not changing. Rank the materials according to their thermal conductivities, greatest first. So which one would have the largest thermal conductivity? C, right. So C has, yes, the largest temperature difference. So here it's 10 and here is -5. So there's a temperature difference of 15. So that would actually have the lowest thermal conductivity. Yeah, so it's the other way around. The largest one would be, I think, these are equal, right? 15 and 10. Yeah, so I think, so D and B are equal top, and that's the second, and that's the third. So I think it would be, yeah, BDAC, like this one. So let's look at that just mathematically first. So, so the formula goes P is equal to K A T H minus T C over L, right? We're talking about thermal conductivity, so let's just rearrange it for K. So it'd be P L over A T H minus T C. So that's the quantity that we're talking about here, and so we get an F2. Hi, do we get an F2? Yeah. So we want this to be large, and these power, the power is the same, right? We're told the length is the same, they're the same thickness, and the cross-sectional area is the same, so these are all the same for every single one of those. So the only thing that's different is this temperature, and then, so actually, to make this large, you need to make this small, right? So that's why the smaller temperature difference is the largest thermal conductivity. Okay, so that's a mathematical explanation, but a more physical explanation is, compare like having, say, a material like copper, which conducts heat very well, and then if you have some foam, things that have copper has a large thermal conductivity, but foam has a low thermal conductivity, right? And you use foam for insulation because you want to keep, say, warm inside the house and keep the cold out, right? And so the foam is effective when the temperature difference is large, right? Like it's outside it's 0 degrees, but inside your room it's like 25 degrees. You want that to be large. If it's bad insulator, then heat is coming in from the outside, and the temperature in your room is 5 degrees, outside it's 0, right? So the temperature difference, you want the temperature difference to be large for something with a low thermal conductivity, right? So if it has a low thermal conductivity, the temperature difference should be large, which is why the material with the lowest thermal conductivity is the one with the greatest temperature difference. So this is like, it's -5 outside, but it's 10 degrees inside your house, right? So that's a low thermal, has low thermal conductivity, so it has a large temperature difference. And conversely, if you made a house out of copper, the temperature of your room would be the same as temperature outside because it has a high thermal conductivity. Okay, so, alrighty. So that's induction, and then we learn in primary school that heat is transferred by conduction, convection, radiation. We're not really going to say much about convection. Probably already know what it is. You heat up something, and if it's a liquid, then there's sort of the liquid actually moves around due to the heat, because like hot air rises or the hot fluid rises, and then the cold fluid goes down. So you're heating the pan at the bottom, but then the cold fluid keeps on going down, right? So it actually tends to transfer the heat around. Okay, so I won't say much about that. And then finally radiation. So I think in primary school I was confused. I got conduction, I got convection. That made sense. But what the hell is radiation? So radiation is basically heat transferred by light. Really, it's just light, right? I call light anything that's not just light that you see, but light that you don't see as well. So as you know, there's infrared light, ultraviolet light, all the way down to radio waves and things like that. So basically all that's light, generally electromagnetic radiation. And light carries energy. This is the only way that you actually get energy from the sun to the earth. Obviously there's nothing between here, there's no materials, there's no conduction, there's no convection, of course. So it's entirely some kind of light that's hitting the Earth, and that's heating up the Earth, right? And so basically anything that is at least above absolute zero, so basically that basically means everything, is always emitting some light. It's always glowing. We don't notice it. Everything in this room is actually glowing, but we can't see it because it's not really at the right wavelengths for our eyes, right? But of course, if you heat up something very hot, of course we know it glows, right? Like, so if you heat up this bit of iron, then it glows red hot. And so, we know that hot things glow. It's just that we don't notice it most of the time because usually the type of light that it's emitting is, so there's a so-called black body radiation curve like this, which we're not really going to study it so much, but basically there's some kind of peak in the wavelength of the light that is emitted. So this is wavelength and this is the intensity. So imagine that this is this thing. So we can see this light that's coming off, this red light, because there's as you make things hotter, the peak of this graph tends to move to the left, right? So it's usually all the way down. The peak of this graph is somewhere like here. So if you take anything in this room, the peak is sort of somewhere here, and then in the visible range, it's so dim you can't see it, right? But then as you make things hotter, this tends to move to the left, and then that's when our eyes can start to see it. And then so finally, then we notice, oh, it's glowing, right? And then so when it reaches some temperature, then you can start to see it. And of course, this is how the old type light bulbs work. Right? So what we will do in this course is not so much this black body radiation curve, but this one. This is the Stefan Boltzmann Law. So this is not talking about all the wavelength. In fact, I think it's something like the sum of the entire wavelength that is coming out here. So if we just forget about the frequency dependence, and then just look at the entire amount of power of electromagnetic radiation coming off of something because of this radiation, then you get a formula that's like this. We're not going to derive it, but this is the total power that comes off something due to basically it glowing. So just to say it casually, so this is equal to sigma, which is some kind of proportionality constant. Epsilon is some factor between 0 and 1, which is basically due to the kind of material. It's actually not even probably the material. It's probably just related to the geometry of the object, right? So if you've got something which is kind of bumpy, then it will not emit quite as much power as if it was a kind of a smooth object, because basically you want all the photons or the light to actually be going outwards. If you have some material which has some geometry, then it might emit it, but it might reabsorb it as well. So this is basically the fraction of the photons that are actually go out, that are not just like reabsorbed, right? This is the surface area. So I should write surface area, not just area. So you've got some object, right? So it's a ball. Then the surface area of that would be like 4 pi r squared. And T is of course the temperature. So this is so this is basically the energy per unit time of all the photons that are coming off it. So we can, for example, consider a typical situation like this. So you've got some object, it's got some temperature, presumably it's a bit hotter than the environment, than the room that it's sitting in, and it's going to be emitting all this light, or photons, out from basically every surface that this object has. So it's going to just be emitting it, just like this glowing thing here. So this is a kind of obvious example, but basically everything is actually glowing, right? Just don't notice it. But of course it's sitting inside a room, and well, this thing is hot, so it's emitting a lot of photons, but like I said, everything in the room is glowing, so the photons are coming off the walls, and it's going to actually hit this object too. So it's actually going to be absorbing some of the photons that are coming off just its surroundings. Yeah. So the kind of thing that you sometimes calculate in this situation is, so the radiated power is that's the photons that are coming off, the orange ones here. But then this is the absorbed power because of the photons that are coming off the room. And then, this photon might eventually hit this thing and it might get absorbed. And then so there's actually a bit of a net gain, a bit of an input power to this object. So it's not just all these photons coming off, it's actually absorbing some from somewhere else. So sometimes you calculate this net power, which is basically the difference in these two powers, right? So usually, if you're considering something hot here, then this T will be bigger than the T environment, this one. And then so this will be a negative number because it's losing energy, right? It's cooling down, it's emitting power, so it's going to be losing energy. I think this is one of the formulas that I give you in the formula sheet. Okay. All right. So, okay. Let me think. Should we do this one or not? So, all right. Well, let me try and do this example question. So figure 18.27 shows two closed cycles on PV diagrams for a gas. 3 parts of cycle 1, so I guess this one, are the same length and shape as of cycle 2, okay? For each cycle, should the cycle be traversed clockwise or counterclockwise if the net work done by the gas is to be positive, and the net energy transferred by the gas as heat to be positive. Okay, so basically for this one, so remember, so this is just the final question, just to cap off this chapter, by the way. It's not related to this one. So we've got two loops like this. Kind of looks like that. It's the first one. Second one looks like this. Okay. Yeah, so as we PV. So as we learned before, the work done in a cycle like this is the area enclosed by the loop here, right? And that comes about because remember, the work is actually equal to the integral of P with volume. And so when you go in the first leg here, if you go this way, then this will be like the area under this first leg will be the work of this first part, and then you go down, which this is a constant volume process, so the work will be 0. And then when you go back here, for example, then the work will be just this area in this rectangular region. And so the work done in this loop is the area within the cycle here, because basically it's going to be, so if you call this 1, or maybe we should call it A, B, C. So work A plus work B plus work C is the the total work of the cycle. We said this one is 0, but you can see that basically work A is bigger than work C here, right? If we go in this clockwise direction. So then, if you want to make the work positive, then of course we need work A to be greater than work C. So basically, we need this one to be clockwise. In fact, it's actually always clockwise. If you see any loop, and if you want the work to be positive, it should always be clockwise. And so what was the question? For each cycle, yeah. So likewise with the second loop, we need this one to be clockwise in order for the work to be positive. And so the net energy transferred by the gas's heat, Q, to be positive. So in a cycle, we know that the total internal energy change is 0. So basically that means that from the first law of thermodynamics, Q minus W is going to be equal to 0. So in this case, Q is actually equal to W. And if we want the net energy transferred by the gas's heat, Q, to be positive, so it's basically the same, because Q is equal to W. We worked out how to make W positive in each case, and then because Q is equal to W in this case, that's all. So it's the same. Okay, so you should definitely do a few of these PV diagram questions, because this is the classic kind of question that you get for this topic. Okay. All right, so let's move on to the next chapter. Any questions on that chapter? Yep.
What is the energy transfer for the first one?
You mean the internal energy, delta E, or?
Yes, yeah.
Oh yeah, both the same, because these are both cycles, so the delta E in a loop will be 0. Yeah. So it's actually the same for either case. Okay, so seems not catching up. I don't know, it might turn on eventually. All right, so let's keep going with this chapter. Next chapter, sorry. Yeah. Okay, so most likely you know this, but basically, okay, well, what is this chapter about? So basically last chapter we were taking the kind of point of view of, okay, so you have a particular gas, and then we can characterize it by a bunch of parameters like pressure, volume, temperature, number of moles. And this was basically kind of a macroscopic view of the gas. So, at this point, we weren't even thinking anything about the fact that the gas is in fact made up of, atoms or molecules. In fact, people, weren't entirely sure that things were made of atoms, actually until relatively recently. People suspected it for a long time, but people weren't absolutely sure of it until maybe, I think, the latter part of 19th century, right? So this chapter is talking about this more microscopic perspective that, gases are in fact made up of a bunch of atoms. We have this picture of gases, of course, today, some balls flying around. And so this is, so interestingly, you can actually make some connections to that macroscopic theory that we just had of pressure volume to this microscopic theory. So this is basically going to go through some of those results. Okay, so because we're going to be talking about molecules and atoms and things like this, so we should get some definitions straight. You probably already know this very well from chemistry, but so Avogadro's number is just a convenient unit of number of atoms. Obviously, in any kind of sample size that we're going to be looking at as humans, where humans are gigantic in comparison to atoms, and so anything that we look at is actually we're picking up huge numbers of atoms every time we anything that we're dealing with in daily life. So Avogadro's number is just a convenient unit for giants such as us. So 6 times 10 to the 23. So this is kind of typical number of atoms that you might find in a gram of some substance. Well, it depends on the substance, of course, but just very rough order of magnitude. And then so we call that unit a mole. So 1 mole is just basically the number of atoms, but in these units. And then so molar mass is basically the mass of 1 mole of this substance. So if we have a mass of some amount of mass, then we can work out how many moles this is by simply dividing by the molar mass. And we can also convert this to the actual molecular mass, i.e. the actual mass of 1 molecule of this substance by basically this molar mass is just the Avogadro's number times by the molecular mass. So again, you've probably seen this before, I hope, but this is one of the central kind of results of the macroscopic theory of atoms. So the ideal gas law, so if you have pressure, volume, number of moles, and temperature, then these are related according to this very compact formula. So PV equals nRT. So, most of this sort of makes sense in a way. Just, if you imagine a container of gas, if you, increase the volume, then the pressure goes down. If you heat it up, then the pressure goes up. Or if you have a flexible container, if you heat up the gas, then it will expand. So most of these things are relatively intuitive. Obviously, if you have more amount of the gas, then the pressure, because you're putting in more material, more of the gas, then the pressure will go up. Alternatively, if you've got a flexible container, having more of it will expand. So all these are, kind of relatively intuitive, and it's all summarized by this formula. And R is the proportionality constant in this case. Now we can also write this R in terms of Boltzmann's constant. So in this case, instead of writing it as a number of moles, we can actually write it as the number of atoms or molecules. Okay, and then there's definition of Boltzmann's constant here, which is R divided by Avogadro's number. And so it's somewhat, the gas constant, but sort of per molecule, right? So it's kind of different units, if you like. And so instead of little n here, which is the number of moles, this is large N, which is the number of actual molecules. Okay, and so we worked out in last lecture, or last chapter of chapter 18, the work done by gas is the integral of the pressure with the volume. So we can work out, using this ideal gas law, what the work is, right? So we know that P is PV equals nRT, so in other words, nRT of V. So, oh, sorry, I should say that this, we're going to look at three different kind of situations. Three cases. So the first one, we can look at a constant temperature process, and this is where we can use the PV equals nRT relation. So for constant temperature, if we substitute the PV equals nRT relation into this integral, and if the temperature is actually constant, then we can actually evaluate this. So nRT over V, and well, number of moles is usually constant, R is definitely constant. And if we're saying that this is a constant temperature process, then all this stuff comes outside the integral. We just have to integrate 1 over V, and then 1 over V integral is log V, and we're going to integrate from some initial volume to some final volume. So this is going to be nRT by log Vf minus log Vi, and then just using the relationship of logs, we can also write it as this. So for constant temperature, we can actually work out literally sort of the work that is done. We can actually just evaluate that integral. In a PV diagram, we can see just by basically plotting this relation that the pressure and the volume are sort of inversely proportional to each other. I think I mentioned this in the past lecture. So 1 over V kind of looks like this, and all these things are just constants here, but say larger the temperature, the larger this factor here, right? So this would be high temperature, and this would be like a low temperature. But so these are so-called isotherms in this PV diagram. And so basically what we've just done here is just to integrate, for example, some region here. This is the initial volume, final volume. This will be the work done by the gas for an isothermal process. Okay. Right. And so I think we already know from the previous chapter that, so if we're looking at a constant volume process, then volume doesn't change, so work is equal to 0. So we can just see that from this integral. So if volume doesn't change, work is 0. And if the pressure is constant, then we know that the work in that case, the pressure is itself constant, so this pressure will just come outside of the integral. So for constant pressure, work, so P dV, but P just comes out, and then it's just integral of dV, and then this is just Vf minus Vi. So in this case, the integral is very easy. We can just take the difference of the volumes. So basically, I think this one maybe also appeared before, but so the new one here is this constant temperature one. So basically combining the ideal gas law, we can actually get an explicit relation for the work. Okay. Right. Okay, so let's try this question. So an ideal gas has an initial pressure of 3 units and initial volume of 4 units. Table gives the final pressure and volume of the gas. Okay. Which processes start and end on the same isotherm? Right, yeah. So you mean C, like answer C here, right? Yeah, yeah. Yes, that's right. So initial pressure is 3, initial volume is 4, right? And so from our PV equals nRT relation, so the initial pressure and volume, so basically initially, so whatever this thing is, nRT is equal to 12, right? Because P times V is 12. Now finally, we're talking about the same, so same isotherm. So same isotherm means that the temperature is the same. So the final temperature must be, of course, just 12 over nR, whatever that is, right? So basically, any of those where the P times V is going to be equal to 12 is going to be on the same isotherm, right? So that's A, B, little a, little b, and little d, and little e. Okay. Right. So this is the first kind of taste of connecting this microscopic theory to the macroscopic theory. Okay. And so what we're going to try and do is to actually derive this PV equals nRT relation. So previously, we were kind of just given it as a phenomenological formula, right? So, like I was saying, you know, you've got a balloon, you heat it up, expands, so forth. You know, if it's really connected to the microscopic, you know, world, then maybe we can actually derive this thing from the point of view of, you know, this is a bunch of atoms that are actually flying around in this balloon or box in this case that we're going to do. And so let's try and figure that out. Okay, so I'm just going to sort of sketch the kind of approach here. And we're not going to be able to fully derive the PV equals nRT thing, but we are going to be able to get some way of the way there so that we can actually actually make some interesting conclusions. Okay, so what we're going to think about is a situation like this. So we're going to think of a box. So this is the container for our gas. Okay. Our box has some dimensions like this. L, L, L. Okay. Let's roll the other side of the box. And what we're going to picture here is that there's a lot of atoms that are flying around in this box, right? So it's say 3 atoms, and they are going to be flying in some direction, and let's say that the velocity of them is v. And what we're going to do is try and figure out what the pressure that is exerted on the walls of this gas is due to these atoms flying around. Okay, so that's basically the approach that we're going to take. We're going to say, okay, these atoms are flying around, they're hitting the walls, and that's going to be the origin of this pressure that we're talking about. Okay, so to start off with, I'm going to make a kind of a simplifying assumption. It's not very realistic, but let's just consider this atom here, and suppose this, we're just going to look at this atom here, and what this is going to do is just bounce between the these two walls on the right and on the left here. It's just going to bounce back and forth in a straight line between these, this side, and we're not going to think about the fact that the atoms might collide into each other or anything like that. We're just going to say, okay, this particular atom here is bouncing back and forth, left and right, and it just does that forever. Okay. So let's work out what the pressure on this one is. So to work out what the pressure is, well, pressure is force over area. Okay, and well, we can see that the area is L squared. So why don't we already say that? So force is L squared. Okay. Now we need to work out what this force is. And we actually did something very similar to this in, I think, chapter 8 or 9. And remember, there was some example like this. There was something like there's a stream of balls coming here, and then there's something here, and then the balls bounce off, and we have to calculate what the average force on this object here is. Remember that question? Yeah. So the way that we did that then was something like this. We said, okay, well, the actual force that's actually applied on this wall here, kind of looks like this, right? It's a bunch of collisions, right? So it goes boom, 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 like this, right? And every, some time period, there is some force that is applied on the wall. But what we can work out is that actually, like the, say the momentum change. So the momentum change, say this bounces, say this is something that's moving with some velocity v, and each one of these things has some mass m, and say it bounces off the walls at the same speed. Okay, so the change in velocity here was like 2 mv, and then we can work out that the average force was going to be equal to change in momentum divided by the time interval here. So in this case, it was whatever like the time interval here is. So it was going to be 2 mv divided by, well, whatever this time interval is. So that's basically what we had before. This was kind of like the average force if you sort of smoothed out all these spikes to some value. Okay, so we had this result here before of force average is equal to change in momentum, which is in this case 2 mv divided by t. So we're going to use that result here. So it's 2 mv divided by delta t L squared. And so we have to work out what this time here is in this case. So the time in this case, well, it's going to hit this wall every, we're talking about just this wall here at the moment. So the time interval that Okay, well, maybe you guys can tell me. What is the time interval? Assuming that this just bounces back and forth here. What is the time interval of it hitting this wall? Assuming the velocity is v. So how often does this one, which is just going horizontally, how often does it hit this wall? What is the time interval between strikes on this wall? Velocity is v. This side is L. There's no acceleration, constant velocity. Yes, yeah. L divided by V, but remember it's like two, it needs to go back and forth, right? It needs to hit this one. So it's actually 2L over V, yeah. So this is going to be 2L over V. Okay, so let's stick that into the formula. So this is on the bottom, so 2mv squared over 2L cubed. These twos cancel. Okay, so now we actually have a bit of a start of a formula here, and so it's saying pressure should be something like mass of this atom times by the velocity squared divided by L cubed, and L cubed is obviously the volume. Okay, so let's say this is volume, and then let's also convert this to the moles. So what have I got here? So that's number of, yeah. So okay, no, sorry, not yet. Okay, so we've got mv squared over volume. Okay, so this is little v, this is big V. Okay, that was the pressure due to one atom, but of course, so maybe I should write just like one atom here. But if, I don't just have one atom here, and I have lots of atoms, right? So if I've got n atoms, then it should be n times mv squared over v. And this is looking good because, as I said, we're kind of trying to derive this PV equals nRT relation, right? And so we've got P now, actually. We've got V, right? And this kind of looking kind of right because this, if you put this on this side, it's going to be PV. And then now let's get our N. So if we convert to number of moles, okay, so let's do it like this. So this is the mass of one atom, right? And from the first few slides, the mass of one atom, yeah, that's little m. We can relate that to okay, maybe it's just easier just to work it out ourselves. So mass of one atom is related to the m is the molar mass, right? So mass of one atom times by, this is the total number of atoms in the sample. So this is basically the total mass of all the atoms, right? Because it's just n times m, little m, which is the mass of all the atoms. And the total mass of all the atoms, you could equally work out from a number of moles by just saying, okay, how many number of moles are there, and then work out what the, and then just put in the molar mass instead, right? So there's the number of moles you have times by the molar mass, which is like the mass of 1 mole. So it's just like different units, right? So total mass is big N, little m is equal to little n, big N, okay? So we can turn this into something like this. Okay, so we've got P, we've got V, we've got N. Okay, we're not going to be able to get RT, I'm sorry. But we got quite a long way here. There's one more thing that we need to actually do, which is to fix up this assumption that this thing is only going left and right on this wall. And of course, there's no reason why all the atoms are just going left and right. Right? Actually, all the atoms are going in random directions. And so, in fact, it's not just left and right. In fact, it could be in any direction. And if you look at what we've got a quantity v squared here, right? And if you look at the total velocity squared, of course, this is equal to Vx plus Vy squared plus Vz squared. And actually what we really did here, maybe what I should really have said is something like, this is something like Vx, okay? Now so maybe, maybe I should change the notation. Okay, all right, fine. Let's do it like that. So it's Vx. So this is actually Vx, right? Because it's only going left and right. Now there's an argument to say that there's basically no reason to say that any x component, y component, z component are going to be bigger or smaller than each other. So basically we can assume that Vy squared is going to be the same as Vz squared, which is Vx squared. So for, so Vx squared is actually going to be 3Vx squared. And then we can relate just this x component of velocity as being a third of the actual velocity of the system, of the atoms rather. And then so let's stick that in, and then we're going to get n m, the actual velocity over 3v. So the final result got a bit squished down there, but that's basically how you get that. Okay, so it's a little bit of a long derivation there, but just to kind of show you that you can actually go quite a long way in terms of getting this PV equals nRT relation. We can't quite get temperature, but we could get the P, we got the V, we got the little n. Yes?
Why do we use pressure equals force equals PA rather than the P equals nRT?
Oh, because PV, we're trying to derive PV equals nRT actually.
What's the difference between P equals F divided by A and P equals?
Well, this is definition. I mean, that's what pressure is. Pressure is force over per unit area. So, definitely pressure is that because that's how pressure is defined. PV equals nRT is, maybe the way I think of it is just a phenomenological relation that people just experiment with gases when in the lab. and said, okay, well, what if I double the volume? You know, what happens to the pressure? What happens to the temperature? And then they figured out that relation, but it's not derived, right?
So it's just different.
Yeah. And here we kind of attempted to derive PV equals nRT. We got, I would say, like 75% of the way there, because actually we got something that looks a lot like PV equals nRT, but it was not. We couldn't get a temperature, but a lot of it looks quite similar. Yeah. Okay. So, okay, but it's not a total failure. In fact, it gives us something very interesting. Okay. So we couldn't derive it, but now let's combine those two formulas and then see what that seems to tell us. Okay. So on one hand, this the kind of the microscopic theory is telling us this, that basically PV is equal to n of mv squared over 3, okay? And then the macroscopic theory is saying PV equals nRT. Okay? So this must mean, apparently, this thing here, these are equal to each other, okay? Because we kind of use two different techniques to get this. So let's see what that actually tells you. Well, if we equate these things to each other here, then we will get v squared is equal to 3RT over m. So let's see. Yeah. So this is so-called, well, okay, if I take the square root. This is the so-called root mean square velocity. Root mean square basically means the square root of the average of the squared velocities. So actually means that you calculate the average of v squared and then you take the square root of that number. So it's sort of like, yeah, it's taking the average of the squares is, of course, something different to taking the average itself, right? So, so for example, you've got a histogram of, different. So this is the probability, and then let's say these are like exam score results, right? So okay, so let's make it easy example. So the average. This is the test results, right? So we did a quiz in the class. This is how many people got 3, this is how many people got 4, this is how many people got 5, right? So obviously the average would be like something like 4, right? So the average is, of course, let's say one person got this, 2 people got that, and then 1 person got that, right? So then it'd be like something like 3 plus 2 times 4 plus 5 divided by 4, right? That's the average mark. But the average squared mark, average square, would be doing something like this. 3 squared plus 2 times 4 squared plus 5 squared, okay? So that's the average of the squares, right? Obviously, it's going to give you something different because you've got the squares, right? Okay, but so the root mean square mark would be square root of this thing. So 3 squared plus 2 times 4 squared plus 5 squared divided by 4. Okay, you're not going to get the same value as what you got here. Okay. So this is what root mean square means. It's just the average of the square. And why are we averaging over the squares? Well, because actually when we got this formula here, this had a square in it, okay, and because that's actually the quantity in question, that is actually the thing that we should be averaging over. So that's why this thing will not really be the it's not going to be the average velocity. It's going to be the average of the squared, but then you square root that. Okay, so all right. Anyway, that's sort of a technicality. So let's. What's most important here is that what's quite interesting is that this velocity is only dependent upon the temperature, really. Okay, so assuming you got your material, whatever the gas is, it's just some gas, right? So the mass of that, the molar mass of that is just some value. R is a constant, right? But this thing is only dependent upon the temperature. So what that actually tells you is that when you heat up a gas or you cool it down, what you're really doing is you're just changing the velocities, actually velocity squares, of the atoms. That's all you're doing. You're just speeding them up or you're slowing them down. And, well, that kind of makes a lot of sense because, well, we know that the energy of something like this is something like half mv squared, right? So essentially what you're doing by heating up a gas is that you are just, if you increase the temperature of it, we can view it as we're just changing the kinetic energy of the atoms. Or speeding them up, right? So, right, so if we take that point of view, then, well, let's work out what the kinetic energy of the gas is of, say, a single, single atom like this. So the kinetic energy is going to be half mv squared. Okay. And let's put in this value, this velocity that we just found. So it's going to be half of, this is the mass of a single atom, this thing squared, 3RT over m. And this was the molar mass, right? That's the mass. This is the mass of 1 mole of substance. And that's related to the mass of a single molecule just by Avogadro's number. Okay. So let's just stick that in there. So then it's going to be 3 over 2. And then when you put that there, this little m cancels. And R over NA T. And R over NA is what we define as the Boltzmann constant. Like this. So what this is saying that it's actually even more incredible in a way, that the kinetic energy is it's not even related to the mass of the atom anymore, right? So this mass actually, the little m here, that's the mass of the atom, just cancelled out, and the kinetic energy is really only dependent upon the temperature. It's not even related to the mass of the atom, which is kind of amazing in a way. So really this temperature is really a direct measure of the kinetic energy of the gas. And so why should that be? Well, imagine, you've got a box of something, and say you've got some heavier balls in it and some lighter balls in it, right? And then you got some heavy balls, light balls, and then you're just like going to jiggle it like this, okay? Now, as you can imagine, the heavier balls are not going to bounce around so much, and the lighter balls are going to bounce all around in the box, okay? And this is basically because it's harder to give the heavier balls, more velocity. The heavier balls are not going to fly around as much because they're in the same box, and you're sort of giving all these balls the same kind of forces and the same kind of energy, actually. And so basically, because this is a random process, you more or less give each of the balls the same amount of energy, right? Because it's kind of random. But because the heavier balls are heavier, they're not going to move as faster, but they're still going to have the same amount of kinetic energy because, half mv squared. So the heavy balls, this is larger, but their velocity is going to be smaller. So really the thing that's actually important is not so much like the speed of the balls or the mass of the balls, but it's really like just how much energy they have. And when you've got this container and you're just jiggling these things around, basically all the balls have the same amount of energy. The heavy balls or the light balls, they have the same amount of energy. They just move in different ways because of the kinetic energy formula, but in terms of the energy, it's the same for the heavy or lighter balls. That's basically what's happening in this case. This kinetic energy formula it's independent of mass because, the masses cancel out here. And eventually it's only related on the temperature. And the temperature is basically the parameter is like, this is how much energy that the whole system has. So really, it's kind of an interesting, interesting kind of conclusion that you come from all this, which is that, given temperature, all ideal gas molecules, no matter what their mass, have the same average translational kinetic energy, and it's like 302 kT. When we measure the temperature of a gas, we're basically measuring the average translational kinetic energy of its molecules. So basically the take-home message is this, which is that temperature is really a direct measure of the average kinetic energy of an atom. So when you touch something and you go, oh yeah, it's hot or cold, you're actually just measuring or you're feeling the kinetic energy of the atoms there, right? So you're a kinetic energy sensor. When you're feeling hot or cold, that's actually what you're measuring, which is kind of pretty amazing in a way. We started off temperature being a rather kind of abstract thing. We just defined it because I know stuff is hot and cold, so let's just put a number to it. But actually, it turns out that it's actually absolutely fundamental quantity. That it's really not just something that is something that our body senses and it's sort of an ad hoc thing. It's actually completely fundamental because it actually really measures the energy. It's direct, it's basically the same, right? Temperature is just the kinetic energy of the atoms, just up to some constant. Okay. All right. So gas mixture consists of molecules types 1, 2, 3. molecular masses, M1, M2, M3, M1 is the heavier ones, M3 is the lighter ones. Rank 3 types according to average kinetic energy and then speed. Okay, so let's do A first. So M1, M2, M3, which one has the largest average kinetic energy? Yep.
That equation, K equals 0 to KT, is applied for as microscopic world.
Well, we actually, yes, that's exactly it. Sorry, yes. That's right, because this is the mass of a single atom. And you can kind of tell if it's macroscopic or microscopic according to what constant it's using. Ideal gas law is a kind of a macroscopic thing. This K, which is R divided by Na, is Boltzmann's constant. This is a kind of a microscopic quantity. You can tell because it's divided by Na, which is a really big number. Yeah, so this is energy per atom, single atom. Yeah. Yep.
R is same because it doesn't depend on.
Yep, that's right. Yeah. So that's the whole thing. That's what we've been talking about for the last 5 minutes. So kinetic energy only dependent on temperature, nothing else. Not the mass. Doesn't matter what it is. It's got the same temperature. It's got the same kinetic energy. Okay. What about the RMS speed? Which has the largest RMS speed? Root mean squared, that's this thing. Yeah, the first one, yes. So it's just half mv squared, right? So we've established they all have the same kinetic energy. So the lighter it is, the higher the velocity is. This needs to be the same. So if this goes down, then this needs to go up. So that's going to be the fastest one, followed by 2, followed by 3. Okay, all right. Maybe that's a good place to break. So we'll continue on Thursday.